Pre-Calculus Chapter 6, and in Chapter 6 we're going to look at a few applications of the trigonometry that we've been working with over the last couple of chapters. The first application that we want to look at in Lesson 1 and 2 here are the vectors and vectors in the plane. Now, when we talk about temperature, distance, height, area, volume, these types of measurements, all we need is one number to represent the magnitude or the size of these particular measurements. One number does all of the work for us. When we're talking about force, though, or velocity, acceleration, some of these physics things that you've probably run into, there's two measurements that need to be communicated when we're talking about force, velocity, acceleration, and these types of things. There's a size of the force, and then there's also a direction to the force. Which direction is the force acting, and then how big a force is it? And in a coordinate plane, there's an infinite number of directions that the force could be headed. And so we need a way to represent the direction, but also represent the magnitude of these particular measurements. And it turns out that if we're working with vectors, that we can represent both magnitude and direction by using two numbers that you've seen before, just applying them in a different way. And then a lot of the trigonometry that we've done with these two numbers before still applies because we're still talking about the same two numbers in the coordinate plane. So these two numbers, you're probably asking, well, what two numbers is he talking about? And hopefully that's what you're asking. If not, maybe you are asking now. The two numbers that we're talking about is an ordered pair. Now, in the past, we've used an ordered pair and an A value and a B value in parentheses to represent a single point in the coordinate plane. We're going to use those same two values, but we're going to use them to represent not just a point, but to represent an arrow that goes from the origin to that point. So we're still going to use the points coordinates A and B, but we're going to enclose them in these greater than or less than symbols, and in doing so we're representing or we're indicating that we're now talking not about a single point in space, but we're talking about an arrow that goes to that point with its origin, or with its tail at the origin and its head that ends at that point, or a vector. So a vector is an arrow that goes from the origin to that particular point. So we're going to use the ordered pair, and we're going to indicate that we're talking about a vector by using these symbols. Now, it's important to notice that where the arrow begins is called the tail, and where the vector ends, that point at which it ends, where the arrowhead is, that's called the head. That's very important when we talk about the head minus tail rule here in just a moment. So very quickly, I want to cover a few vocabulary terms that you need to be aware of when we're talking about vectors. When we're talking about two-dimensional vectors, in many cases we'll use the letter V to represent the vector. When a vector is given in the form where it has an ordered pair in these greater than less than symbols, this is called the component form of the vector. Each value in that little symbol, the A is called the A component, the B is called the B component. So there's two components to it, and we'll be working with how do we figure out or calculate each component in order to come up with the vector. The standard representation of a vector is an arrow that goes from the origin to that point AB. So again, we're going to use those coordinates. The length of the arrow is what we call the magnitude. We'll talk more about that in just a few moments. The direction that the vector is pointing is indicated by this ordered pair. Because only one line can go through 2 points, if we have a point at 0, 0, and then we have another point in space, this AB, there's only one arrow that can go through that. So we can very precisely give the direction of the vector by giving the standard representation of its AB components, and then we know that that's the head and the tail will be at the origin. A zero vector is a vector that has the component 0, 0. It has no direction and it has no length, and we really won't deal a lot with that in this in what we're dealing with. Now, Let's talk a little bit about vectors. Any two arrows that have the same length and point in the same direction are actually representing the same vector. Two arrows that represent the same vector are considered equivalent. So in this diagram we have here, we have this arrow that's in, or this vector that's in standard position. Its tail is at 0, 0. Its head is at 3, 4. And then we have another vector here that has this endpoint of negative 4, 2 and a head point, or another endpoint at negative 1, 6. Now if this arrow is the exact same length as this arrow, and if it's pointing in the exact same direction as this vector, then they're considered to be actually the same vector. Well, how do we figure out if this is pointing in the same direction? Well, we're going to use what we call the HMT rule, or the head minus tail rule. If you take the head component A and you subtract the tail component A, that will give you the A component of the vector. Okay, so head minus tail. So the head A minus the tail A will give you the vector component A. And then if you do, this is for A, and then if you do the same thing for the B component, the head minus tail will give you the B component. And in doing so, you'll then have the vector, and you'll have the components of the vector in standard form. And so if you end up with the same components, then you're talking about an arrow that's pointing in the exact same direction. So if we did that with these two vectors here, we know that this vector here is going to be the vector 3, 4, because its tail is at 0, 0. So 3 minus 0 is 3, 4 minus 0 is 4. So this is the vector 3, 4. It gives us the direction. There's only one vector that can go from the origin through the point 3, 4, and that's this one, and has this length. Now the question is this the same vector? Well, we take the head, and remember that's the arrow, so we have negative 1 minus a negative 4, which gives me an A component of 3. And I take the B, a 6 minus 2, and that gives me a B component of 4. So the component form of this vector here is also 3, 4. So this arrow is actually pointing in the exact same direction as this one. And the length of this arrow, as you'll find out later when we talk about the magnitude, is the exact same length as well. So if I have the same components, doesn't matter where that arrow is in the coordinate plane, we are talking about the same vector. So if an arrow has an initial point of 2, 3 and a terminal point of 7, 5, what is the actual vector? So I'm looking for the components. The initial point is 2, 3, so that's where the arrow begins, and the terminal point is at 7, 5. So the question is, what is this vector? So I want the components. So I'm going to do head minus tail. So the A component is the head component 7 minus the tail component 2. 7 minus 2 is 5. The B component is 5 minus 3, which is 2. So this is actually representing the vector 5, 2. So these are the components of the vector that have these 2 points as its initial and terminal points. Okay? Let's take a look at the second one now. Here we have an initial point of 3, 5, and I'm given the components of negative 3, 6, so what's the terminal? Remember, it's simple algebra here. The head minus the tail gives me the component. Okay? And so if I want to find the A component, I simply substitute in. So I'm given the initial point. Now remember, that's the tail. That's where it begins. And I want to know the terminal point, the head. So I'm looking for this A point. So I'm going to simply substitute in the values that I'm given into this little equation and solve for the one that I need to know. So initial point of A is 3, so that's going to be 3, and the component that it gives me is negative 3, so the question is, what's the head point's coordinate? So I just simply do a little algebra, add 3 to both sides, so the head point is 0. And then I'm going to do the same thing for the B component, head minus tail. So this is the tail, so minus 5, equals the component of 6. A little bit of algebra gives me 11. So the head point, or the terminal point, of this particular vector is 0, 11. Now I can double check that very quickly by doing head minus tail. 0 minus 3 is negative 3, and 11 minus 5 is 6, so that gives me the components of the vector that I'm given. Okay? If P is the point 4, negative 3, and PQ represents the vector 2, negative 4, what's Q? So PQ, so this is the ray, and from geometry, because this is listed here this way, P is my initial point, and Q is my terminal point, because in geometry, when we name a ray, the terminal point or the initial point is always first. So this is PQ. So then I'm given the point 4, negative 3, and like the problem before this, I'm given the component or the vector components as 2, negative 4. The question is, what are these components then? Okay, and these are the components of the head. This is the tail. So again, I'm simply going to use head minus tail to give me the component. And I'm going to substitute in. So the head is what I'm missing, minus the tail of 4 gives me the A component of 2. Adding 4 to both sides, I get an A of 6. So the coordinate of Q is 6. And then I do the same thing with the B component. So the head component is unknown, B minus a negative 3, it giving me a negative 4. So adding 3 to both sides, or subtracting rather, I get a B component of negative 7. So this is the coordinate of this point should be 6, negative 7. So actually this arrow would be pointing the other way. But again, this is just a diagram to help me figure that out. And again, I can quickly check this by doing head minus tail. 6 minus 4 is 2. Negative 7 minus negative 3 is negative 4. Okay, so that's how you determine the direction of the vector. In the next video, we'll look at some algebra of the vector, and then we'll look at the magnitude.